Oh, thanks. Whoever turned that on, thank you, I forgot. Just okay. So that's something I'm going to call step number 0. So read the question carefully and then summarize what's given and what needs to be found. You'll see how I do it, and it will be clear for you what you need to do. So, and what's unknown. And as you know, sometimes that information is hidden in words rather than numbers. Okay. And draw a picture, diagram, graph, whatever is applicable. Sometimes more than one of these. Okay. I don't recommend putting numbers in your picture. Just put symbols. The symbols are explained in step number 0. Okay, so the idea behind steps 0 and 1 is to extract all the information from the text, from the statement of the problem, so you don't need to refer to it ever, that you have everything compactly summarized on your paper or screen. And then decide which equations may be relevant. I'm emphasizing the word maybe. It's better to overdo than underdo. So if you think that equation is remotely relevant, just do write it down. I could say do the math, but let me elaborate on number 2 a little bit. Okay, so how do you decide which equation is actually relevant? Well, every equation has a bunch of symbols in it, right? A bunch of variables. Some of them are given, some of them are not. So let's say you have an equation that looks a plus b equals c, just some silly equation. And then you take your red pencil and go through this, look at the table in step 0, and put check mark next to quantities that you don't that you do know, and question marks next to quantities you don't. And then you'll see exactly like what's possible to use, like what equation is useful, what equation isn't, and so on. Okay, so this is a helpful technique. Again, after some mastery, you may not need to follow it in too much detail, but in the beginning, at least, I'll urge you to follow this procedure until you get some mastery. Okay, after you did the math and you get your answer, or answers, things don't stop. So you need to check your work or check your answers. So what does it mean? So for example, in math, when you solve equations, the way you check them, you just plug things back in. That's fairly straightforward, and this is pretty much all you can do in math. In physics, there are many more ways to control whether your answer makes sense or not. And we'll discuss those things. We'll probably dedicate 1 or 2 separate lessons just to that, because as you suspect, given the format of the F equals MA competition, that's a multiple choice answer, it becomes a very useful skill to be able to determine which answers are certainly wrong, because you try to rule out some obviously wrong answers. So this will be a useful technique, but you can obviously use the same exact technique to check your answer, right? If you got an answer, you use the same evaluation technique to see if your answer makes sense, if it's reasonable, if it's not reasonable. Okay, and we'll learn quite a few methods here. Let me just list some of them. So again, my enumeration may sound funny here, but I'm going to call it method number 0. Just plug your answer back into equation. That's obvious. That's what you do in math. Okay. So this is basically checking your math, but then methods 1 through, I don't know, maybe 5 eventually, will be actually using physics and some common sense ideas to control your answer independent of your math. Okay. So the thing that we'll start using pretty much right away will be unit analysis. It's especially helpful if you got a symbolic answer, then you can check that the symbols you got for your answer, their unit, it has the right combo. Order of magnitude. We'll use it today as well. Physical sense. So again, we'll practice it. It only really applies, well, yeah, only applies to symbolical answers. What that means is basically you have some expectation as to what the answer should do if you increase or decrease one of the givens, one at a time, right? So if you say increase, you know, if you drop this pen from a certain height and you measure the time it takes to hit the table, that time should increase if you increase the height, right? That's obvious. But when you got your answer, you express the time in terms of the height as a variable, and you can tell if mathematically that's consistent with your intuition. If you increase the height in your answer, does the time increase? Does that make sense? So this is what we'll call physical sense. And finally, for now, we'll talk about more methods as they become applicable. But for now, I'll just give you one more, considering limiting cases. That is, if you solve a more general problem, but you happen to know the answer to some less general or more specific problem, you can check if the new answer, if you put those symbols in the answer to some specific values for which you know the answer already, if that is consistent with what you know. Once again, let's say you make the pen slide down a frictionless ramp at a given angle, theta. You got some answer that depends on theta, then you know the answer for, say, theta equal 90, because that's just exactly the same thing as simply dropping the pen. So in your formula that involves theta, you put theta equal 90, and you see if this limiting case answer agrees with the old answer. Okay, you guys follow so far? So this is limiting case. Limiting cases are a big thing in E&M. So you'll see we'll use them a lot. Okay, so this is it for now. Do you have any questions about anything on this slide? Okay. So let me play with units a little bit just to give you a flavor of like how powerful unit analysis can be. And then we'll play these games from like every once in a while. So let's say, so this is what I'm going to talk about here is using units analysis not to check the answer, but actually try to guess the answer. Okay. So here is that problem that I just described. So you have a ball that's falling from a given height h. You want to find the time it takes to fall. And let's say v at the bottom, just before hitting the floor. So the velocity just before the hit. Okay. So how do I approach this problem? Let me just explain. Usually I would ask for your contribution, and it won't be just me talking all the time. But for now, let me just explain so you're clear what I'm talking about here. So first off, we're not just given the height. We're implicitly given the acceleration of gravity. So we can safely put it in the givens. And that's what I recommend you do every time you deal with gravity. Okay, so the unit analysis method is trying to play with the givens to construct just the right unit combo for the unknown and claim that that should be roughly the answer. And we'll see in what sense roughly is. The idea is fairly straightforward. So the first step is to write out units of every given and unknown. Sorry, my pen is behaving. Given and unknown. Oh, and by the way, for brevity, we'll be using this notation. If you want to say units of x, this is how you will write it. Just bracket x. Because I'm too lazy to write all these words all the time. So units of x. Okay, so we have h, g, and t in the first part of the problem, and h, g, and v in the second part. So in the first part, we'll write out all the units. Units of h are meters. Units of g are meters per second squared. Units of t are seconds. And of course, you can do the same thing for the second part. Meters per second. Oops, sorry, what am I doing? Meters, units of g are meters per second squared. And units of velocity are meters per second. So what we're allowed to do in here in this simple game is to multiply, divide, raise to power, including fractional and negative power. So we see we need to get rid of meters. That means we need to divide h by g or g by h. And a more close look will tell you that it's actually h divided by g that'll do, right? So if you do h over g, you indeed cancel the meters and you get seconds squared. And then the next step you see that, oh, okay, in order to actually get seconds, you want to consider the square root of that, okay? So if you do square root, you get seconds, okay? And this is exactly what you want for the time. So you say, okay, time seems to be equal root of h over g. Now, I suspect a lot of you actually know the right answer. Tell me, is this the right answer? Folks, that's a question for you. And I see some people, it's solved by constant, but yeah, what is it?
Well, I mean, he did say proportional.
Okay, true. So let me, yeah, I agree. I put it safe. So let me, and I apologize for the background noise. Okay, so it's off by a constant. So what is that constant?
√2. So it'll be 2h over g.
Okay. Yes. Thank you very much. So I'm putting it in red. Okay, so this is actually one and only drawback of this method. Units analysis cannot tell you a numerical factor because it carries no units. But it still gives you a good idea what's happening. And we'll come back to this in a minute after we finish with the velocity. So what do we do with velocity? Using the same game, it looks like if we multiply h and g, we get meter squared per second squared. So if we then take the square root, we get what we want. So we take square root of h times g, we get meters per second. So we're trying to claim that v is root of the gh. And again, you can probably tell me I'm missing something.
√2.
Exactly. So we were missing √2 as well. So again, we have to live with that. Unit analysis cannot get this. But some other evaluation methods actually can catch things like this, especially limited case methods. That's why they're so powerful. Okay, anyhow, I was gonna say that even though we cannot get the precise answer using this method, let me put it this way. We get like 90% of the answer. We know what the answer should look like in terms of variables, but yes, we don't really know what the numerical constant factor is. However, there are questions that you may still address correctly and precisely without even knowing this numerical factor. For example, if I asked you, okay, now if I double the height, let's say I dropped it from some height and it took me a second, took the pen a second to drop. Now I double the height. How long will it take? So it's like a
√2
2 times
seconds.
longer.
Yes.
2 times longer.
Uh-huh. Yeah, you're thinking faster than I'm writing. So T1 is 1 second, and let's say H, now we double the height. H goes to 2H, and T goes to √2 seconds, right? It goes by a factor of √2. Same with velocity, right? Velocity goes to √2 v. Let's say, what if you go to the moon and drop from the same height? What will happen to the time? What do we know about moon?
Gravity is weaker.
Okay. You happen to know by what factor?
I'll guess 1/4.
Close, but not quite accurate. Yeah,
1/5.
Six.
Just kidding.
6. Okay, so the gravity on the moon is 6 times smaller. What does it mean for us for the time? How will it take longer, shorter, and by how much?
It'll take 6 times longer, or √6 times longer.
√6, yes. Be careful, exactly. So √6 seconds in our case. And what does it imply for the velocity?
It'll be √6 times slower.
Uh-huh. So 1/√6 v1. Okay. You see, you can answer all these questions without even knowing this constant, because it never really shows up. When you talk about proportions or scaling is the word here, you don't need that constant. Okay, much like, let's say, if you have a round cake and you double the radius, how much larger is the second cake?
It's gonna be 4 times as large.
4 times as large. And it's true no matter what the shape actually is. If you think of a square cake, if you double its size, the area quadruples. If the cake is round, you double the radius, the area still quadruples. But the constants are different, right? There is a pi involved for round things, but you don't care. As long as it's the same in both situations, it just cancels out. That's in case you never thought why, like, say, pizzas or round cakes are priced not linearly with the radius, right? They don't tell you, they usually put it like, okay, 6-inch cake, 9-inch cake, and so on. So the price is not 1.5 times the smaller one. It's bigger than that, right? Because it's proportional to the area, which in turn is proportional to the square of the radius. Yes, so scaling technique is something we'll use all the time, okay? So let's maybe do one more thing, and then this time I'll ask you to play with the units just to see how well you got this. Period or frequency, rather. It's easier to work with the frequency of a pendulum. Again, I suspect that many of you have taken mechanics, have learned oscillations and know the answer, but pretend you don't. So here is the pendulum. And you deflect it by some small angle. Okay, assume the angle is really small. If you don't know why it's important, let me just tell you, and you have to take my word for granted for now. In a few weeks we'll get to that more accurately. For small angles, the period and frequency do not depend on the angle, and this is called harmonic oscillator. Does everybody know what frequency is? Okay, and we'll also, in the context of oscillations, we'll mostly talk about angular frequency. So that is denoted by omega and is related to period through this equation, right? T is the period, omega is the angular frequency, and this is 2 pi. So let me make it a little bit more open-ended here. Our ultimate goal is to find omega. Okay. By the way, what are the units of omega?
Hertz?
Rads per second.
Oh, I know. It's radians.
Radians per second. I'd say.
Radians per second, but the radian is actually unitless, so we can just say 1/2. But we don't call it hertz, right? Hertz is reserved for regular frequency.
Oh yeah, for regular.
Which is 1/t without the 2 pi. Okay, now I made it open-ended, so you folks tell me what you think may be relevant, what quantities may affect the frequency or the period, and I'll put them down here.
G, L, and M, where L is the length of the string and M is the mass of the bob.
Okay, so you told me 3 things and I put whatever you told me. So let me ask the others, your colleagues. Folks, do you think there are some additional quantities that may affect the answers? If you feel that some of them are not relevant, that's fine. More is better than less. But if you feel that Elvin has omitted something, do let me know. And while you're thinking, I'm going to label this as L, and G is acceleration of gravity. M is the mass of the ball. Do you think Kelvin covered everything? Yeah, with my statement, about the angle, that's it, right? So in principle, angle may affect the answer, but like I said, for small angles, it doesn't. And small, let's say, smaller than 30 degrees. Okay. So who wants to go over the solution? Feel free to write on the space. Does everybody know how to write on my whiteboard? So if you look at the menu bar on top, you should hit the annotate button. For some of you, it may be hiding under the triple dot that says more. Hi, Alvin. I was hoping you'd put some physics stuff in there. And please talk while you're writing, so that
Oh, I forgot I was muted. My bad. Sorry. So we have the units of g. Since g is just gravitational acceleration, we know that's meters per second squared. Length is just meters, and we have our units for mass is kilograms. Because we don't see kilograms anywhere else in any of the other quantities, and we don't see kilograms in what we need, this might be potentially unnecessary. We can keep it here for now, though.
Oh, that's I thought it was Elvin. Elvin,
Oh.
did you just say hi?
No, that was Leon.
Oh, Leon. Okay.
I'll do the next part.
That's
So
okay.
then if we divide g by the units of g by the units of L, and then so g over L gives us 1 over a second squared. So then the square root of g over L gives us 1 over a second, which is the units for frequency. So we know that the frequency is going to be proportional to g over L.
Folks, what do you think? You agree, disagree, have questions, comments, concerns?
Well, because we have radians also in omega, we could probably say that it's proportional to like root pi g over L. Yeah.
Well, I wouldn't make that connection necessarily.
You know,
because
okay.
So when you're dealing with unitless things, it's really hard to come up with the relationship, because sometimes it may be through a trig function, right? And there are many. All trig functions are unitless, so there is no real control on how they show up. So yeah, angles are tricky to deal with. That's why I had to make that statement for you folks, so you knew that, okay, I don't need to bother with angle here. But yes, this is pretty much it. So omega is indeed equal root of g over L. And anybody knows the right answer here?
I think you multiply that by 1 over 2 pi.
What? Multiply what?
Multiply the entire thing.
By 2
Wouldn't
pi?
it be 2 pi g over L? Yeah, I think it's root 2
Well,
pi g
okay,
over L.
tell me the formula in the box, is that correct? Or is it missing something?
Yeah, it's missing a constant factor.
Well, you will be surprised, but this formula is actually perfect. It's not missing anything. Yes, if you want the period, of course, you need to take 2 pi over omega, right? And then it gets the 2 pi in front, 2 pi, and you flip this, so you get root of L over G. That you may have seen before, and I suspect you've also seen this. The nice part about omega, whenever you deal with oscillations, your best bet is to try to find the unit combo for omega, because omega is quite often just, just the combo without any numerical factors. So again, we have no means of knowing that, but this is precisely the right answer. And again, you can argue what happens if if you don't know that, you have to assume there may be some constant in here, right? Because your method doesn't catch that. But still, you can answer a question like, okay, so what happens to the period if I double the length of the pendulum? So let's understand that. If length of the pendulum doubles, and this is going to be my brief way of writing that sentence. L goes to L is my way of saying L doubles. Then what happens to the period? Josephine, what happens to the period? Josephine, you hear me? You're muted.
Yeah, sorry.
Huh?
I'm not sure.
Okay. Who can explain? So period is given by this last formula here, right? So you forget all the constants. They don't really matter. You only scale the variable that is being scaled, right? So L doubles, that means there is a factor of 2 showing up here, which is under the square root. What that means is that period goes to root 2 times the old period. Does that make sense?
Yeah.
Okay, so the period gets longer as the pendulum gets longer. Oh, and again, you can like think of what if I go to the moon? The gravity is 6 times weaker there. Now let me put it here. So G goes to 1/6 G. What happens to the period on the moon? Can you take this one, Josephine? First tell us, is the period going to get longer or shorter? Anybody can help, but not Alden or Andrew. Somebody who hasn't spoken much yet. Have you seen things like videos recorded on the moon? Do motion appear like? Does motion appear
So Joseph just wrote in the
faster or
chat.
slower?
Yeah, there are answers in the chat.
Yeah, I'm actually getting to the chat right now. So I see Vincent and Joseph put the same thing. They say multiplied by root 6. So let me put it down, and then everybody else tell me if you. There should be an arrow rather than equal sign. Josephine, does this make sense? Do you agree with this?
Yeah.
Okay, yeah, so G goes down, right, and it's sitting in the denominator. So the period goes up. And yes, things appear slower on the moon, right? You've probably seen those videos with Neil Armstrong walking on the moon, jumping. So things appear slower. It means longer time, longer period. And this is by how much it is longer. Okay. I feel that we need a little summary of the scaling technique here. Folks, do you have any questions on this slide? No? Okay. So, yeah, let me summarize the scaling technique. So scaling technique is basically a shorthand technique that can answer questions like by how much, by what factor will this change if that changes. So say y depends on x to some power n. Okay, that you see a lot, right? N can be integer, fractional, positive, negative. So what if your x2 equals some number k times x1? So k is called the scaling factor. Okay, then your y2 will be equal, let's put it, yeah, actually, you know what, let me just do it a little bit more elaborate, and then we'll bring it to a very compact form. So y1 is x1 to power n, y2 is x2 to power n. Now, what you want to address is the ratio. So if you were to consider the ratio, y2 over y1, just, you know, do it straightforward. Let's take this, divide by this, x2 to the n over x1 to the n, which is the same as x2 over x1 to power n, right? And then this ratio is exactly the scaling factor, k. So y2 over y1 is simply the scaling factor to power n. Is this clear? If you look back at the previous slide, what was the power n, say, in the period for L? So if we say that t of the pendulum is proportional to L in what power? Okay, so okay, Leon says 1/2. Okay, so n is 1/2. This is n. And when I said go to the moon, that meant that G goes to 1/6 G, so the scaling factor was what? Well, so, sorry, I'm jumping ahead. Scratch that. So if we say that the length doubles, that means the scaling factor is 2, right? So the period 2 over period 1 is k to power n, right? K to power n, which is 2 times 1/2, which is root of 2. Okay, so this is probably the most detailed way of explaining the scaling technique. Okay, so the shortcut is really to say if x goes to kx, y goes to k to power n times y. Yeah, I don't want to write the subscripts 1 and 2. I say x goes from just x to this and y goes to this. Is this notation clear, folks? Just get comfortable with this, because this is much more compact than what we did here. Yeah, for example, one last example, kinetic energy. We know it's 1/2 mv squared. So if velocity doubles, what happens to kinetic energy?
Quadruple.
Quadruples. And can you tell me what n and scaling factor are?
2.
2 and 2, right? So so let me put 2 squared times kinetic energy. Okay, so this is pretty much how it all works. Tell me if you have any questions about scaling technique, because this is pretty powerful. It allows you to answer things very fast. Okay, so how about taking a break right now, like I don't know, 10-minute break, and then we'll come back and start solving more challenging problems. Okay. You can turn your camera and sound off for now. Okay, can you see my PowerPoint? Okay, great. Is the text large enough? Readable? Okay.
Yeah, it's fine.
Okay. Okay. Take like a minute or read the question and tell me what you think.
Should we private message you?
Are you trying to text me the answer?
Yeah.
Okay. Okay. Okay, got an answer from Vincent. Got an answer from Joseph. Let me tell you, I have some variety in the answers, so it's good. Not everybody agrees.
Wait, so is he going up or down? He's going.
He's always going up.
Okay.
Wait, yeah, he's always going up.
When the
But the
escalator is moving
escalator
up.
may either. so oops. Yeah, so you're given what happens when the escalator is stationary and when it's moving up. You need to figure out what happens when the escalator is moving down. Make sense?
Mm. What does it mean when it says when the escalator is moving up? Like, wouldn't it add to how fast he goes? Oh, he only climbs up 20 steps. Oh, okay, I get it. All right, I misunderstood the question. Okay.
Okay, so far 4 people submitted their answers and I see 3 distinct answers out of the 4 submissions. Maybe let's wait for another minute and then I'll ask some people to present. Okay, 5 submissions. Okay, Vincent, you changed your mind? Abhijit, you changed your mind too? Okay. So if I count the latest submission, I have 5 submissions, 3 distinct answers. Okay. Is anybody else close, or can we start discussing it? I don't want to kill fun if you think you're close. Andrew. Okay. Okay. Let me see who was first with this particular answer. Elvin, you also changed your mind. Okay. So, Joseph, do you mind explaining how you got it? Can you write on the whiteboard?
It doesn't say it. I don't think it says how long he's walking or if he's like doing it from the beginning to the end, the entire escalator. So I assumed that this was in the same amount of time for each of these.
Yeah, I think it's constant step rate.
It's the constant size, right? This constant climb.
And also constant step rate.
Yeah.
Should I present?
Yeah, go ahead.
Wait, was my answer correct? The second one?
Let me not tell you yet.
All right. So the way I did it was the whole escalator is 30 steps, so we know it's 30. And then, oh, that's a bad drawing, but yeah. And when the escalator was assisting him, for every 20 steps he did, it had to have given him another 10 steps. So the rate with the escalator was 20 plus 10 for that time period. And then if it's going down, then it's going to be 20 minus 10. So then that's going to equal 40. And I guess I don't really have units here. I'm sorry, we want this to be 40, but for 20 of his steps is going to be 10 steps up the escalator. So then we want to scale this up by 3. And then we'll have him do 60 steps, and the escalator will make him go down 30 steps, and that'll have him at the top of the escalator. So he has to take 60 steps.
Oh, interesting. Okay, folks, what do you think?
I did it slightly differently.
I agree with
Instead of, oh,
Yeah.
sorry.
you. Can introduce yours first.
Yeah, so instead of for every 20, the escalator does 10, I just scaled it down. For every 2 steps he takes, the escalator does
Yeah.
1. So by that logic though, I did it in like little increments. So I kind of wrote out a few. So here, how do I annotate? Let me see if I can.
Yeah, if you see the menu bar on top.
Here we go.
Yeah.
So basically, he would be taking 1 step and then a second step, and then it would be bringing him up to step 3 with the escalator on. If the escalator is off, he's taking 1 step, he goes up 1 step, and then he goes up a second step, and then the escalator brings him down to this same step where he started originally. And then he has to go up again, and then the cycle will repeat. So it's going to look something like this, 8, 9. So essentially I got also 60, but you're double counting the first and the last step. So you subtract 2 and you'll get 58. That's what I got.
Interesting.
Well, I think it's a constant.
So since you're more than 2% off. Yeah, go ahead. Vijit, you were saying?
Isn't it like a constant for every step you take, it's going to take you back half a step?
Probably. I might have oversimplified it.
I still think it's 60, but I guess we'll see.
I saw that a couple more people think it's 60. So I'm curious to see what they did. So Joseph, you were the first who submitted 60. Do you want to say anything?
Yeah, I also thought about a similar way to others. If there's 30 steps and he only goes at 20 steps when it's moving, that means like he's getting a boost of
Half his speed.
yeah, a boost of half his speed.
Mm-hmm.
So then he's like traveling at 1.5 times the speed. So then you would divide by that. Yeah, you would divide by that and you get 20. But then when the escalator is moving down, he would get half of his speed cut off. So his speed would be 0.5 as much as the original. So you would need to double the amount of steps to 60. That's a way to do it with like rates, I guess.
Okay.
Yeah, I overthought mine. You can just disregard what I did. Mine was a little bit, I took it in increments. It should have been like constant.
Yeah, Andrew practiced discrete thinking. Alvin, you also say it's 60. What was your approach?
I basically, I said that the number of steps, I assumed that each step is like constant. So then I assumed that the number of steps is proportional to the amount of time spent in total. And then I did like a little bit of algebra and then I came up with my answer.
Do you mind sharing or is it too long?
Oh yeah, for sure. So could I have a new page, please?
Oh, you need a new page. We can clean this.
Okay.
And folks, I believe you can save. I didn't tell you, but I don't see that button anymore, but
It's on the top. It's at the very end of the
Yeah,
toolbar.
yes, it's just the toolbar disappeared on me. Where is it?
Wait, should I keep this or I'll clear it, I guess.
Everybody can hit the save if you want that. I'll be saving it as well, but I'm not seeing my toolbar now. Okay, here it is. That's what I'm saying. I have a lot of different windows floating around. Okay, I just saved it. So we can clean this. And it's all yours.
All right. So we can denote the velocity of Rocky as r and the velocity of the escalator as e, right? So then we know that r times t is equal to r plus e times 2/3 of t, because you know, the number of steps is proportional to the amount of time taken. So then, you know, I can cross cancel, and then you move around some stuff. You find that v is equal to 2 times e, right? And then now you're trying to find when is r times t, which is the total distance, equal to v minus r minus e. R minus e times t times some constant factor k, right? So then we can get rid of that. We sub in r equals to 2e. So 2e is equal to e times k. And then you find that k is equal to 2. So that means it's going to take twice the amount of time he took originally. So 30 goes to 60.
Okay. People who had different answers, do you agree or disagree?
Yeah, this is right. This is what I initially had at first, and then I tried to go discretely, systematically, but that's wrong. You should go, it should be constant. I treated it as Rocky goes 2 steps, and then the escalator decides to move down 1 step, and that's not right, because then you do in fact lose steps. So yeah, this was this was the right original response.
Does everybody know who Rocky Balboa is? Okay. Yeah, you know, he practiced.
Boxer, right?
Yes. He did not practice on escalators. He practiced on the stairs of the Philadelphia Art Museum. And there is a statue of him. But yes, he could easily make an originally stationary escalator to actually move down, as Andrew described. So you're not too far off. Okay. Does anybody have any questions? So we've seen 3 very different, not very, but 3 different approaches, 3 different solutions. They all gave us the same answer. Usually, that's very comforting. If you get the same answer by doing 3 different approaches, you probably know you got it right. And this is what I recommend you do, folks, in actual challenge problem situation. Okay, let me save this as well. Let's get to the next page.
Oh, I'll need to join back. I can't see the shared content.
Why?
I'm just gonna need to join back. I can't see the shared screen.
Let me stop sharing. Oh, okay. Folks, can you see the PowerPoint? Okay. So I guess it was just him.
All right, that's better.
Okay, great. So this is the second problem. Again, take a minute, think about it, and tell me what you think. Okay, I see some first answers. Thanks, Leon. Thanks, Vincent. So just to be clear, the coach drives in the same direction as the column. So he's passing them from behind. Okay, I see Ellen's answer. Yes, Leon, that's the whole point. They turn around. Otherwise, nothing interesting happens. Okay, let's give a couple more minutes and then I'll start asking some people. So far, I've seen 3 different answers. Again, it's always interesting when we get different answers. 4th answer, yet different. 5th, yet different. Okay. Everybody has their own solution. No repeating answers so far.
No. Oh, sorry, I'm a bit laggy. Let's see.
Okay, let's ask. Okay, finally we have some repeating answers. Leon was the first person to give that answer. So, Ellen, do you want to explain how you got it?
Me? Okay. So annotate. All right. So there's a thing of length L, right? So then we can use like a relative motion trick, and we can pretend that this is still, while the relative motion of the car is 2v, right? And then whenever the car passes a person, they will start running in the other direction 2v, right? Because you have that's the relative motion of just going backwards at the same speed while going forward. So then now you just want to find the distance that the first person runs before the coach gets to the last person, right? So then the total time that it takes for the car to cross the column is L over 2v, right? But then by that time, the first runner, you multiply that time by the velocity of the first runner to get the total like distance the first runner went. So that just becomes L, right? And then the column was L long originally. So then you just add L plus L equals to 2L, and you get that answer.
Yeah,
Folks.
that's pretty similar to what I did.
Who was that?
That's pretty similar to what I did.
Abhijit, yes.
I just didn't use relative speed.
Yeah, no wonder you got the same answer. But people who got different answers, I'm eager to hear from you.
Well, I messed up my algebra. I messed up the algebra. I did a similar thing, except I think I messed up because I said the runner would be running at the speed v this way instead of 2v. Because the car is moving at speed 2v this way. The runner is stationary, but then the runner decides to run this way at speed just regular v. But I think my algebra just didn't work out there. So I agree that this answer is probably right.
Okay, so your approach could have worked, and I actually want you to finish that because, again, that's an independent method. Always good to have those. So Alvin's approach was to switch to the reference frame associated with the runners. Okay. Since it's going to be a permitting theme for us, let me quickly survey you folks. Is everybody feeling comfortable with relative motion? Put some up if you are, and don't put anything if you don't. Joseph, I didn't catch what you showed. So this is like one-dimensional relative motion. That's pretty straightforward. But of course, we'll be dealing with two-dimensional, maybe three-dimensional relative motion. So we'll have a piece of lecture on that just to make sure everybody's on the same page. Yeah, I like Alvin's and Abhijit's approach. This is probably the simplest way to do it. Oh, Leon, yes. Okay, so okay, so it looks like everybody who had a different answers now agree with this. Good, but don't hesitate to ask questions. Something is still unclear or looks suspicious to you. Okay, just a quick, I know we're on the whiteboard and we're during the lesson, but if this were an actual test, Alvin, you would need to write some words, right? You would not just put like
yeah, of course.
Yeah, you will not just put an equation here. You would say, you know, the distance traveled by the first runner by the time the car reached the other end, right? So folks, in general, put some words. Don't just put some equations. Okay. Oh, okay, yeah, this is problem number 3. Again, take a minute, read it, and tell me what you think. Yeah, so this problem will require some algebra. I don't know of any shortcuts here. If you find some, that would be amazing. And wait, have we lost Josephine?
Is the spacing how long the column is?
No, spacing is the distance between two next neighbors.
Runners, yeah. Okay.
Yeah, 2 runners or cyclists. Yeah.
The observer is moving in the opposite direction of the cyclists and runners, right?
No, actually, it's not given explicitly, but
There be 2 solutions then?
yes, there are 2 solutions. But for now, I want you to focus on the one where observer runs in the same direction as the other people. But yes, Abhijit, for homework, you will consider the opposite scenario. Okay, got the first answer, Joseph. Good. Evelyn, why is there two answers?
Oh, I changed my mind.
Oh, so I should look at the second one?
Yeah.
Okay, quickly. Does your second answer make sense? Oh, okay. It may. Okay, never mind. Okay, just maybe another minute. And I'll ask somebody to explain their solution. Okay, so Joseph, you were the first. So do you want to share your solution with us?
Oh, yeah. So I looked at it from the perspective of the observer.
Okay.
So they should be running at the speed so that they, relative to the runners, she passes those 20 meters in the same time they pass 30 meters with respect to the bicyclist.
Okay.
So the speed difference between the runners and the bicyclists should be in a 2-to-3 ratio because the spacing is also in a 2-to-3 ratio.
Okay. Can you put it in writing somehow so that people can follow easier? I forget. Did you have a pencil that allows you to write?
No, but I can just use
You can
the-
type, you know?
I can just use the screen.
Oh, you have an iPad or something?
No,
Oh, it's touch screen?
yeah.
Okay. Yeah. Okay. But you can also type, you know, if you wish. If you hit the text button, you can type.
So how I thought of it was the time it takes to go 20 meters at n minus 20 kilometers per hour should be the same as the time it takes to go 30 meters at 40 minus n kilometers per hour.
Okay. So you basically set up a proportion now, right?
Yeah, and
So since you're already using red, let me. So basically 20, oops. Sorry, it's behaving. Okay, here we go. Yeah, so you basically say 20 over n minus 20 or 30 over 40 minus n. Okay, right? And you can do the math now. And according to you, what's the answer?
I got n equals 28.
Okay, and Vincent seems to agree with you, but some other people don't. So those of you who don't agree with this answer, what is, by the way, 28 what?
Well, kilometers per hour, right?
Yes.
Right, so how did he arrive at this? He got speed equals n. Wait, can we draw like a diagram?
That's
of
a
what's
good
going on?
idea. Who can who wants to draw a diagram?
I guess I'll draw right here. Oh, that's it.
I mean,
Okay.
I can draw it on a new page.
Okay.
So does everybody who wanted to save it, save it?
I did.
Okay, cool. So I guess I'll I forget, I keep forgetting how to, like this. So clear. Oh, cool. So we have a car. Oh, bicycle, sorry, bicycle. It's beautiful. That's moving at a speed 40 minus n kilometers per hour. And we have runners who are moving at n minus 20 kilometers per hour. And we're saying that they're going to pass like the observer, where that is, who's moving at n kilometers per hour. Oops. And these pass each other at the same time. So this guy covers 30 meters between the next one at this speed in the same time that this guy covers 20 meters at this speed. So if we have like the next person 20 meters away, and here we have the next bike 30 meters away. And that sets up a proportion of 20 over n minus 20, oops, equals 30 over 40 minus n.
Okay.
I hope this makes some sort
Yeah, that's exactly what we had in the previous slide, but now with the diagram. Thank you, Andrew, for illustrating it. Yeah, folks, I strongly encourage you to do diagrams. They help. And I think all of the answers that I received, they made sense numerically. Even if they were not correct answers, they still made numerical sense in terms of evaluation number 2 that we discussed, order of magnitude evaluation, because obviously you expect the observer's velocity to be greater than the runner's velocity and less than the bicyclist velocity, right? Otherwise, the problem would make sense. So the answer should have been between 20 and 40, and all of the answers I've received were in that range. So at least that part was reasonable. If you first got some answer that was outside of the range and you didn't even submit it because you realized it couldn't be right, then kudos to you. Does anybody have any questions about this problem? Okay, if not, let's try to do one more problem and call it a day. So I'm saving Andrew's writing, clearing. Yeah, so you've seen this a couple of times when I blinked. So here it is. Now we were dealing with acceleration. Quick question to everybody before you get into math. Is the ratio going to be 1 or not?
No,
No,
Why not?
because they're moving much
one of them
faster.
is speeding up, whereas the other one is slowing down, and the other one was faster to begin with, so it has to be something that's either a fraction or more than one,
Can you
depending
tell
on
me
which
more
way you take it.
Yeah, can you tell actually what it is? Greater or less than 1?
Find the ratio of the path lanes covered, but well, it depends on which order you take it.
Yeah, if you take first over second.
Oh, search in first. Decrease the impact.
First is the one that went faster originally.
Oh wait, I didn't read it that way. Oops. Hold on. Let me redo.
Okay, so do we have at least an agreement on whether the ratio should be greater than 1 or less than 1? Okay, I got. Who is talking? Leon, can you hear me? Okay. Okay. Vincent, do you want to explain how you got your answer?
Sure. Okay. I just drew a diagram almost.
Okay.
I'm going to use. Okay, so started here at particle 1. So I separated into two times. The first time with the acceleration of 2a and a here.
Mm-hmm.
Second time with a and 2a.
Okay.
So I just use the distance formula. It's d is equal to v it plus 1/2 at squared. So for the distance the particle 1 moves in t time, it starts at 0, both of them. So it becomes a 0 here. And then you have 1/2 at squared. For the first one, you have d is equal to 1/2 times 2a t squared, which becomes just at squared. Yeah,
Mm-hmm.
becomes at squared for the distance. Erase that.
Oh.
Should I not erase that? I need more space.
Oh, you need more space. Okay, let's summarize what you got so far. Let me actually put it down. So you got that D, oops. You got that D1, 1. So D1, 1 equals at squared.
Okay. Should I continue?
Yep.
Just try that. Okay, so d, I guess 2, 1 is equal to, well, it starts at 0 as well, so from 0 plus 1/2 at squared. So d2, 1, it will be just 1/2 at squared.
Okay. Yeah, let me also put that, and you continue in the meantime.
And then you switch, we could do d1, 2. And right now you have to calculate the velocity at this point. The velocity at that point would just be at, 2at, sorry. It will be 2at.
Okay.
And the velocity here would be equal to just at. Okay, and at this point, you just plug back into the equation again. So you have 2at, and then multiply by t again, because that's the time again, plus plus the 1/2 at squared. But now a is just a, t squared. Okay, that gives you 2, and then you can factor out the at squared, but it gives you 2at squared plus 1/2 at squared. And that's d1, 2. So that's 2.5 at squared.
Okay. Yeah, let me put it up here. D1, 2 is 2.5, right?
Yeah.
Okay.
And for the last one, you just do the same thing. If the 2, 2 is equal to at times t plus 1/2 2a t squared. That's going to give you just 2at squared.
Uh, 280 squared.
Yeah.
Folks, what do you think? Do you agree, disagree, have questions, comments?
Yeah, now you just
I agree.
add now at squared to 5/2 at squared to get 7/2 at squared for the full distance covered by particle 1. And then particle 2 would be 1/2 at squared plus 2 at squared, which is 5/2 at squared. So it's 7/2 over 5/2 or 7/5.
Okay.
I read the problem wrong, but I think I might have an easier solution.
Easier than this. Okay.
Yeah.
Go
Let
ahead.
me do it graphically.
Yeah. Oh, that would be nice. Okay. So, folks, let's save it. I just did and clearing it. Go ahead.
All right. Okay. So we have our graph here, right? Let's label some lattice points. So 0, 0, 0, 1, 1, 0, 1, 1, 2, 1, 2, 0. And then, these just are logical things that come after. Okay, so then we can assume that the first particle, the first particle first, so we're plotting VT, right? So VT, like so. So the first particle has an acceleration of, let's just say 2. And then the second acceleration has, the second particle has an acceleration of 1, right? So we can draw these two. And then t is 1, right? And then now for the same amount of time t2, we can say that the acceleration halves, so it becomes like that. And the acceleration doubles, so it becomes like that. And then we can draw our line here because it stops. So now because we know that distance is equal to, right, and this is particle 1 and particle 2. So distance is equal to the area under VT graph, right? So then we can calculate the areas, and then, all right, so we can do that. So for particle 2, the area is going to be 1 plus 1 plus 1/2. And then the second one is just P1. The area for P1 is going to be P2 plus, and then the area of like this parallelogram thing is going to be 1. So this is going to be 2.5, which is 5/2. And this is going to be 7/2.
Yeah.
And then you just get 5/7.
Okay. Hold on a second.
I read the question wrong before. But yeah.
Yeah. Go ahead.
Oh yeah, no. I disagree. Yeah.
You disagree?
No, I agree.
Oh, you
I
agree, okay.
with this method.
Okay. Yeah. Let me just check. P2. What is P2? Is this the area of the parallelogram?
Oh, sorry.
Or-
So I guess I can
It's the
label
distance from P2,
a little
particle
bit.
2.
So this is
Oh, P2 plus 1. So you say, oh, okay. So you're finding the difference. Is that?
no, I'm finding wait. So distance is area under VT, right? So then the area of P2 is this from triangles and squares, and the area of P1, the area under P1 is going to be the area under P2 plus this part, and yeah.
Oh, just that the black part or the orange part?
Yeah, the one you shaded as well. So like this.
Okay. So, and you're saying that this is 1.
Yeah.
Okay. Let me see if this is an easy thing to do. Okay. The base is 1. The two heights
Times
are
1.
1s, and there are 2. Okay. Good. Very good. Nice. This is pretty neat, actually. I like it.
Yeah.
And now, since again we got the same answer using 2 different methods, that's comforting. And this is indeed the right answer. So folks, I encourage you both approaches. The first one is kind of solid, but I would say a little bit lengthy. Graphical one is very transparent. You see what you're doing. You just, again, need to do careful things with areas.
I think the problem is the graphical solution would only work for like very simple changes like this one. Like if we add in like 2 other changes, the other solution would adapt a little bit better than this one.
What do you
Really,
mean?
I
You
think a
get-
graphical one would actually adapt better because what if you had polynomial to
And then
represent
just
the
take piecewise
acceleration? Then
integrals. You can
yeah,
just take piecewise integrals, and then
yeah, I think
True.
this way is the more adaptable way.
Okay, folks, I like what you're doing right now, because normally I would have to say all these words, but you were thinking in that direction already. Yes, so every time you learn a method or use a method, you think, okay, when is this better? When is that better? So in this problem, I would say they're kind of comparable. Maybe graphical is a bit faster, okay? But yes, you're right. The analytical method becomes easier if you have some non-trivial function of time, like polynomial or whatever. So Andrew, you were mentioning changes. Did you mean like the numbers are not as nice?
I mean, like the first particle acceleration can now be written as 3x plus 2 times of the original acceleration or something like that. Yeah, so more of a polynomial change.
Okay,
Well,
well,
then if it was a polynomial change, I think the graphical would be better.
for polynomial, graphical, I mean, you know how to compute areas under polynomials. That still requires integration, right? So yeah, again, f equals ma, I don't think it actually goes into non-trivial accelerations.
Last year it had like a question that required calc.
Really? Okay, so for some reason it's not up yet. If you happen to have a copy, that would be great if you could share with us.
It's not up. Oh. Let me check.
I checked this morning again and it's not up. It only goes to
That's such a long
2019.
time passed. Oh.
Now, folks, how do you feel about these problems?
I feel
Do
pretty
you
good
find them
about
interesting? Do you find them challenging?
Yeah,
Or is it too easy?
they're interesting.
very interesting.
I think we could use like a little bit of practice on like
Okay,
a
so
few
if maintain
tricks.
V dvdx.
Well,
Oh, that thing.
uh,
That was annoying.
what is that problem about? Is that something I should know?
It was on the
Like the
29th.
V dot
DVDX
thing.
problem. Oh, from one of those problems I gave you in the beginning of spring.
Yeah.
On the past test.
Here's the past test along with the solutions. Oh wait, is that the B? That's the B. I didn't take the B. The A. Let's see if I can find the A.
Where
I
is
remember
it?
the B.
I may have gone to the wrong place. I only saw exams up to 2019.
Oh, I didn't like go on the site. I just searched it up with the 2020 and it showed up.
Oh, nice.
I guess their foldering is just bad. They probably just organized it wrong.
Okay, let me just. Okay, here we go. Well, I got it. I'll look at it.
Oh yeah, the A is out as well. You just changed the A to the B to an A. Yeah, that's
Okay.
the one we took. Yep.
Okay, please remind me what's the significance of A and B? Is it two different versions?
The A is the first one, the B is the second.
Or one
And
we know.
number 3
Oh,
requires
yeah, there were
calc.
two.
Number 3 required calc.